So this is theorem 2.4.1. It says if, so let us say what is given, right? Suppose f is defined as above, quadratic with a positive definite Hessian with a unique optimal solution. Number 2, S1, S2, Sn are a set, are forming a set of conjugate directions to G, and recall G is the positive this is G. So if if these two conditions are true, and if x1 is any starting point in Rn, and number 4, x2 is equal to x1 plus alpha 1 s1, where alpha 1 is the solution of exact line search on F along direction S1. Okay, so these directions are already given to us, and these directions are forming a conjugate set of conjugate directions to G, and I'm doing exact line search on these directions. Okay, then so after making so many assumptions, then what is the result we will get? Xn is actually going to be x star. So that means I will be hitting the optimal solution, and nowhere I am inverting G. All right, in getting this xn equal this xn. Okay, all I'm saying is, suppose magically somebody gave us all these conjugate directions with respect to G, so G inverse is somehow implicit in these conjugate directions. So if those directions become known to me a priori, then I just have to do line search n times, exact line search, not inexact line search. Then I will get the optimal solution in n steps. Moreover, if I look at any intermediate step while doing these line searches, so maybe in the third iteration or the fourth iteration, I get a nice point in the sense that xk plus 1 is the minimizer of f in the subspace generated by x1, so starting from x1 and s1, s2 up to k. Okay, so for example, let's take k equal to 2. So what result number 2 is saying is you start from the point x1 and let us say direction s1 is going somewhere along this direction, and s2 direction is going somewhere like this, and they don't have to be orthogonal to each other. So then what this result is saying, you start from x1 and do some line search along s1, and this is your x2, and then starting from x2 you pick direction s2 and do a line search along s2 direction, and maybe you reach x3. So what this theorem is telling us is if I try to minimize the function by looking at over all points, which can be obtained by so look at all points. Let's not use alpha, so let's say gamma, or gamma is also taken. Let's take beta 1 s1 plus beta 2 s2, and I'm free to choose any beta values. This x3 is going to be minimum for this function over all possible beta values that you can pick. Okay, so essentially what it is saying is that in this example x3 is going to be the minimum of this function in 2 dimensions. Okay, let's take a step back and try to understand what this theorem is saying. So recall that G is positive definite. We can show if G is positive definite and S1, S2, Sn are a set of conjugate directions, then S1, S2, Sn must be linearly independent. Okay, so the proof is similar to the case when S1, S2, Sn are mutually orthogonal, but now, as we said, conjugate directions are not too different from orthogonality, so it is rather easy to prove this. Okay, now since these are linearly independent, that means if I look at beta 1 S1 plus beta 2 S2 plus beta n Sn and look at all possible combinations of beta, that means I will cover all points in Rn by choosing different values of beta. So that means what this theorem says is that by inductively moving from case n equal to 1 to n equal to 2 to n equal to 3, we can show that this x n plus 1 is actually going to be the minimizer, global minimizer of my quadratic function f. All right, so this is a nice method then. So here is the outline of the method then. Starting from x1, pick a direction. Let's say S1 is the steepest descent in iteration 1. Do exact line search. And find x2, and then pick s2 equal to minus of g2 plus something something, which we will talk next, and keep doing this forever, and then repeat. And this is really my conjugate gradient method. Okay, so the trick is to find this extra term in finding this S2. Okay, and the motivation for finding this S2 is coming from this conjugate gradient, which makes sure that at least when the function is positive, definite, quadratic, then we should be able to converge in a fixed number of steps, not in the limit, not when we do many iterations like in steepest descent, but in n iterations I should be able to converge for a quadratic with positive definite Hessian, and then I can use that method for more general functions as well. Okay, so what we can see from this method is, so recall that when we do exact line search, if we do exact line search, then the gradient at the next point, so S1 is the search direction in the first iteration, and then the G2 is the gradient at x2 must be equal to 0, and this is true at every step. Is n minus 1 transpose g of n. Okay. What we will see later is that these conjugate directions actually have a stronger version of this property, in the sense that gk plus 1 transpose sj will be 0. So this is part of the theorem 2.4.1. So we can also show for positive definite quadratic case that gk plus 1 transpose S1 is equal to gk plus 1 transpose S2 is equal to so on and so forth up to k, they are all 0. Okay, and this is something we would like to replicate for general functions also when we try to find these S directions. Okay, so recall that in the theorem that we just discussed, these S directions were already given to us. The main question is, how do we find these S's without computing G inverse or doing complicated things with the Hessian matrix G. So so this is what is answered by the Fletcher-Reeves method.